What we decided for this line integral and calculating values of the vector field at all these points along this curve is that we're going to calculate the dot product of, the function and a vector in the direction of the curve C. At each point along the curve C, we'll find the dot product of the vector field and a direction vector along the curve. Let's start by describing the different direction vectors that we have. The delta R, the dr that we're going to get in this first part of the curve, the horizontal part of curve C, is going to be some small change in x in the I direction, but no change in the j direction. So, because it's all motion along the x direction. Then after we make our turn, our delta R will be no change in the I direction plus some small change in the j direction. That's how we break up the curve from 10-1 to 10-10. We're just going in these little directions. These little delta R's are all these little vertical vectors. From 1-1 to 10-1, our delta R's are all small changes in the x direction, little delta xi's. So let's call this horizontal path. Let's go along the horizontal path and calculate the line integral. So let's first look at the horizontal part of C. We're going to calculate the dot product of the vector field F, and the vector field F is negative I plus 2j dot the delta R, or dr, dot delta xi plus 0j. So here's the dot product that we're calculating. It's just a vector dot another vector, so it looks like we're going to have a negative 1 times delta x plus 2 times 0. So we'll have negative 1, deep space, negative 1 delta x plus 2 times 0. So we're just integrating the function negative 1 dx. We're going to integrate. In this case, we want to integrate over all the values. Since we were able to write this dot product all in terms of our x variable, we're going to integrate all the values of x. So we're going to integrate as x goes from 1 to 10. So we get, this is 9, so negative 9. Any questions? Finding the dot product of the vector field and a little piece of the direction vector. Let's look at, and we got this negative 9. Let's see what's this negative telling us. Notice that in this first horizontal part, we're going against the vector field. The vector field is pushing against us, and it's like we're flying into the wind. So our little bird is flying into the wind. And so we got a negative value. Since I just phrased that way, let's think about what will happen as we go from 10-1 to 10-10. Now our direction is mostly in the same direction as the vector field. So let's make the calculation for the vertical part of C, which is the green part. So on the vertical part of C, we're going to make a similar calculation. We're going to take the vector field, which is always minus 1i plus 2j, and find the dot product with the delta r on the vertical part, which is no horizontal movement, all vertical movement. So find the dot product of minus I plus 2j and 0i plus delta y times j. So the dot product here is going to be -1 times 0. So we're not getting that part, -1 times 0. That's not telling us. That's giving us no change in the x direction, plus 2 times the delta y. Notice that the I and the j drop out. We're calculating a dot product. The dot product of a pair of vectors is a scalar. So what we're integrating is 2. Delta y is going to become a dy in our definite integral. And we'll integrate over all the values of y that are in play. And so we're integrating. See, this is why I shouldn't copy these problems off of Wiley. Because we're integrating from 1 to 10 again. Dang it, Wiley. Wiley, why did you let me fall for that? It's my own fault. We're integrating over all the values of y that are in play, and y goes from 1 to 10. So we're integrating these values of y. So if we integrate 2 from 1 to 10, we're going to get a positive 18. So let's see how this makes sense with our bird flying through the wind. In the first one, we had a negative value because we have the curve pushing against the vector field. But in the second leg, even though we're traveling the same distance, even though we're going the same distance, okay, now it makes sense. All right, Wiley, I'll let you off the hook this time. We're traveling the same distance from 1 to 10, but now we're flying with the wind. Furthermore, the wind is at an angle. So the wind was pushing against us less on the horizontal parts, and it's pushing with us, so it's positive, and there's more of it because it's 2 in the y direction and just -1 in the x direction. So -9 on this first leg of the journey, and positive 18 on the second leg of the journey. On the first one, the vector field is pushing against the curve. On the second part, the vector field is pushing with the curve. And with different magnitudes, even though the length of the path was the same. So the vector field is pushing against the curve. The vector field is pushing against the curve on the horizontal part. We get a -9. The vector field is pushing with the curve on the vertical part. The vector field is also more vertical than it is horizontal. The vector field is more vertical than horizontal. more vertical than horizontal. It's got a 2 vertical and only a 1 horizontal. Any questions? That seems like a lot to think about, because not only are we trying to integrate, not like mathematically, not only are we trying to put together our new thing, vector fields, with our new thing, parameterized curves, we're trying to incorporate our calculus thinking in this new environment. Fortunately for our heroes, the calculus thinking is still the same. Integration is multiplication, in this case, a dot product, where one of the factors is variable. I made both things constant in this case, which is why we got to get away with multiplication in both calculations. So let's think about where this is headed next. The next stage would be to do this process, but maybe at all the points we don't have the same vector field. Maybe the vector field is no longer constant. That's why we're going to have to integrate things. And instead of the curve being so easy to describe, all I direction or all j direction, what if the curve is going at some wacky angles at different points? That's why we're going to have to parameterize it. That's why we had to look at the velocity vectors. As here we have r is going to be a position vector, so the derivative of r is going to be a velocity vector. It's going to be pointing in a direction. There's a lot to take in. There's the moving against the vector field on part of the curve and moving with the vector field on some other part of the curve. Any questions? Great. This is where multivariable calculus finally starts to get interesting, when we start getting into vector calculus, because up to this point, all we've been doing is describing stuff. So now we're describing some brand new things, and we're making some interesting calculations. All right, let's pause the video here and talk about what's coming next.